Hello everyone, welcome back. This video is going to be a review of chapter 2, which was when we first learned derivatives. We started with the formal definition, and then you learned all your rules like chain rule, product rule, quotient rule, and we talked about tangent lines, and then we finished, I think, with implicit differentiation. So that is what we're going to be covering. So first thing we learned was what is the formal definition of a derivative. And so the derivative, f prime of x, you can see I wrote something here. I just tried to start this video a second ago and I messed up too many times on the first thing I was writing, so I did a fresh start. So the derivative of f of x will equal the limit as change of x approaches 0 of f of x plus change of x minus f of x over change of x. So what this comes from is that definition of slope you've learned before. This is like y2 minus y1, and then this is the change of x, x2 minus x1. But we're wanting that change of x because it's like the slope between 2 points, but there are 2 points that converge to be like a single point because that change of x is approaching 0. So that's the idea behind the definition of a derivative. It's the same idea as slope, but those 2 points that you're finding the slope between become 1 point, and you find the instantaneous slope. So when you see this on your AP test, they don't normally use change of x. They replace change of x with h. So you could also write this as the limit as h approaches 0 of f of x plus h minus f of x over h. That is probably what you'll see on your AP test. So what does that mean? Is because we already have our trick, so you don't really have to use this, but how they'll want you to use it is they're going to give you something that looks like this format, and you have to know that this limit is going to equal whatever the derivative of the function is. And so sometimes that x is going to be a number and your answer will be a number, or sometimes it's going to leave it in terms of x and your answer will be a function, a derivative. So if you look at this one, you can see they left x as an actual variable, not a number. So I tend to have y'all look at this first term. Oh, now that should be similar, but only because when that's a number, it tends to mess y'all up. So it's not always as obvious as in this example. So that x plus h is like what they plugged in for x. So I replace x plus h with like a big x. So that is my original function, sine of x. So I know my original function is sine of x, which I know you could get that here, but again, in a different problem, it's not going to be as obvious if you look at the second term. So then what is my limit? It equals f prime of x. So if f of x is sine of x, the derivative is cosine of x. So that whole limit will just equal cosine. Could you get that using L'Hopital's rule? Yes, but you have to think about h is your variable in this problem. So that's sine of x when you do the derivative of this term. That's going to go away. So that's where using L'Hopital's rule on these problems is going to be an issue. So next idea is the slope of a tangent line and slope of a secant line. So we don't use secant line that much, but they could talk about it on your test. So it's just a line that crosses through 2 points on the curve. So that means that you can use the average rate of change. And so that is the slope that you learned back in the day, y2 minus y1 over x2 minus x1. The calculus way they write that is f of b minus f of a over b minus a, but that's the same formula. So whichever one you want, and that would be the slope, right? I should have put to calculate slope equals. And what that would look like on a graph is, let's say you just have some quadratic, and here's A, here's B. Oh, well, I didn't line that up very well, did I? A was supposed to line up here. I'm going to change my A to B here. Drawing too fast. And here's my B. Then the slope of my line, I would just use this formula, do f of A minus f of B over B minus A. I think I said that backwards, didn't I? Okay, so now what if you wanted the slope of a tangent line? So this which would be not the average rate of change, but the instantaneous rate of change at a single point. So instantaneous. So which is another word for that is derivative. So that's why we associate derivative gives you slope. If there's anything you should know, you know derivative gives you slope at a point or of a tangent line. But ultimately it is this slope at a point. So to know its slope, to calculate slope, you can't use this because you don't have 2 points. So you have to take the derivative and plug in x. It equals f prime of x at whatever point you're talking about. So we could say f prime of a, because then when we do our graph, we'll draw that same curve, and we'll say if a is right here, and I want to know the tangent line would go along that, just technically cross through at that point, no other point. It might look like it because you can't really get too close right there. But if I want to know the slope of that, this line, this tangent line, it's going to be whatever f prime of a is. Okay, so how do we know? Oh, let's read this, it's important. If a function is differentiable at a point, it is continuous, but not the other way, right? So if you know your function is differentiable, what does that mean? You just can take the derivative. If the derivative exists, then it has to also be continuous, but just because it's continuous doesn't mean the derivative has to exist, because at these 2 spots, at a sharp turn in a vertical tangent line, it is continuous, but it's not differentiable, right? A sharp turn is going to look like a V or something along those lines, where it switches slopes real fast at a point. A vertical tangent line is going to look when it like switches concavity right there in the middle. And then also jumps because it's not continuous, right? So you're not differentiable at sharp turns, vertical tangent lines, and I'm actually going to change this to say and when it's not continuous. So there's 3 spots is not differentiable. Sharp turns, vertical tangent lines, and whenever it's not continuous, wherever you have a discontinuity. Okay, so now here's your basic rule. So at this point in the video, I would highly suggest pausing, and doing these is just kind of like a quick review of all your rules. There's nothing, just all you're doing is finding the derivative using your normal power, product, quotient, chain. Now I'm going to actually work them out, which is going to make this video kind of longer than it needs to be, but feel free to fast forward and just check your answers real fast. So number 1, y prime, when you're taking derivative, you bring your exponent to the front and multiply it by the coefficient. So because it's just a 1, that would be 250 times x, and then you subtract 1. So that becomes 249. I'm going to label these because it might get messy. I'm going to do them out of order. Number 2, it's just a bunch of power rule. So bring your coefficient to the front and multiply it by the original coefficient. So 5 times 4 is 20. X to the power of, subtract 1, 4. So you bring it to the front first, then subtract. Minus 6x squared. This would just leave you with plus 7, and then the derivative of a constant is 0. Okay, on this one, if you're multiplying, you could go 2 different routes. You could actually distribute this and multiply it out, and then just use power rule, or you can leave it, but you would need product rule. So for product rule, it's the original second. I try to make it match quotient rule. The original second, so I'm going to call that G. I'll call this F and this G, times the derivative of the first plus, and then switch it, the original first times the derivative of the second. So if we do that here, the original first, is 2x cubed minus 5 times the derivative of the first would be 6x plus 4 plus, now switch it, the original first times the derivative of the second, which would be 6x squared. And now you could clean this up if you needed to, right? We could FOIL this out distribute this out, this term to all three terms, and then you could add and combine all like terms. To save time, I'm not going to do that. If you did it and you want to check it, oops, sorry, let me know. I don't have the answer in front of me because I was not prepared. I wasn't thinking. But I can get the answers and write them down if you feel like you want to check your algebra simplifying. Okay, number 4, you would need quotient rule, right? And on this one, I don't think you could get around it. So what is quotient rule? It's you start with the original bottom. I'm going to come over here and write it so I have room. Which I'm going to call the bottom G and the top F. So the original bottom times the derivative of the top minus, switch it, the original top times the derivative of the bottom, divided by the original bottom squared. So it matches this, but it's minus, and then over the original bottom squared. I remember you start with the original bottom on the top and bottom. So if we do that on this problem, start with the original bottom, times the derivative of the top, which would be 12x minus 5, minus the original top times the derivative of the bottom, which would be 6x. That's it. I thought there was going to be more. All over the original bottom, put it in parentheses, squared. And again, you could multiply, FOIL this, distribute this, subtract, make sure you distribute that minus sign if you're going to simplify it, and leave it. I would not try to divide this out or anything. Okay, J-Mac, stop ruining the professionalism of my videos. Okay, number 5, look at that. What would you need? It would be chain rule, right? How do you know? Because you have something inside something else, which is because you have something in parentheses, really. If you can take the derivative of something inside parentheses or a square root, then you need chain rule. Which the formal way to write chain rule is you start, if you have, I'm trying to figure out where to be the best place to write this. If you have f of g of x, then the derivative is you take the derivative of the outside, keep the inside the same, times the derivative of the inside. That's how you write that. So if we do that for number 5, so when you do this first term, that 12, that 5 is like a coefficient in front, so you're going to bring that 12 to the front and multiply by the 5. So it's going to be 60, keep the inside the same, minus 1 would be 11, times the derivative of the inside now that you kept the same, so that would be 6x squared, because minus 1 is 0. So that was the derivative of this, then the derivative plus 4 is also just 0. So that is how I would leave that answer. Now if you wanted to, you could multiply the 60 and the 6x squared, but you would not be able to distribute it to the inside because it is being raised to the power of something. Okay, number 6 is just, you know the derivative, e to the x is e to the x, right? So the first term would be 10x. You keep the coefficient when you do derivatives. So that's going to say minus 2 e to the x times the derivative of the exponent, but that's just 1. And then plus 1 would be 0. 7. Now this is all in the exponent. So when you do derivative of exponential, you keep it the same, times the derivative of the exponent. It's chain rule. The inside is the exponent. So that'd be 4x plus 7. And I would just leave it like that. And then lastly we have 8, which by the way, we didn't learn e in natural log till chapter 5. So if you're looking for more on that, you would want to go to those notes. So the derivative of natural log is 1 over the inside. And you got to do times the derivative of the inside. So 1 over 6x squared plus 5x minus 11 times, what would that be, 12x plus 5. And then you could write that on top of your fraction if you want. I don't have much room, but So I'm going to leave it like that. So those are your basic derivative rules. Now let's review our trig derivatives. So these are ones you just really have to memorize. Now we did, I think, do tangent. I don't know why they're not all 6 there. We'll have to write some more in. We did learn how to find the other ones in, I think, chapter 5. But honestly, I would just memorize. So the derivative of sine is cosine. The derivative of cosine is negative sine. So find a way to remember that. And then the derivative of tangent is secant squared. The derivative of secant is secant times tangent. And now we have 2 more, right? I don't know why they're not here. The derivative of cotangent and the derivative of cosecant, CSC. Oops, sorry. This isn't staying very nice and neat. So cotangent is negative cosecant squared. And then cosecant is negative cosecant times cotangent. So I kind of remember like tangent and secant have, like kind of go together, and cotangent and cosecant kind of go together. I don't know if that makes sense, but help you kind of memorize it. But the main 2 are these 2. If you don't have a good memory, at least get these 2 down. Okay, so for tangent line, right? When it asks, anytime you see line tangent or tangent line, your mind should automatically go to point slope form. You are not using the actual equation. You're writing an equation for this line. We don't care about the function. We just care what is the equation for this line. Okay, so you're not going to have to take well, you do need the derivative for the slope, but you shouldn't be doing antiderivative for sure. So you're going to find the derivative, because that derivative is going to give you the slope. So you plug in your x1, that's your c, your x1, to find the slope, which would be your m, and then find y1 by plugging c into the original, which you don't always have to do that. Sometimes that's given. Let's say sometimes given. And then you write it in your point slope form. So here's an example. It says find the tangent line to this function at f of 1. So that is your x value, 1. So we're going to first find our derivative. I'm going to come up here and do it. So my f prime of x would be 6x minus 4. So I'm going to plug in my 1. So f prime of 1 would be 6 times 1 minus 4, so 2. So that is going to be your m, your slope for your point slope form. And now, did they give us our y1? Do we know what f of 1 is? No, so you need to plug it into the original. Find f of 1, which would be 3 times 1 squared minus 4 times 1, which would be 3 minus 4, so negative 1. And that is your y1, and that's your x1. So once you have your x1, which they should give you, y1 and m, you just put it in point slope form. So y minus negative 1, which you could change that to plus, you don't have to show that, equals your slope, which is 2, x minus x1, which is 1. You can clean that up if you want, or just leave it like that. That's up to you. If you want to solve that for y, you can, if that bothers you. Okay, last topic was implicit differentiation. So if you remember, this is when your x and your y, it's not just y equals. If it's just y equals, you can use your rules, but if your x and y is all intertwined together, you're going to do implicit differentiation. So what you do is this is where you take the derivative of every single term of each side of the equal sign, and then because it's dx on the bottom, anytime you're taking the derivative of y, you're going to have to keep your, you can walk by, it doesn't record that. Because you're taking the derivative of y, and this is with respect to x, you're going to have to write dy dx every time you take the derivative of a y term. So if you want to write that down, you can pause the video and write down what we just said. So let's do this first example. The derivative of the first term would be 3y squared, and then we have to write our dy dx. You don't have to put it in parentheses if you don't want to. Minus, this term would be 8y. You got to keep your dy dx. Equals, x to the 5th would become 5x to the 4th. And you don't need to write dy dx because it was in terms of x. Plus 12x cubed. And again, you don't need it there. So then our goal is to get dy dx alone so we know what our derivative equation is. So if you remember, we collect all our dy dx on the left side, all our non-dy dx terms on the right side, so then you can factor out a dy dx. So if you look, we already have it set up, right? All our dy dx terms are on the left, all our non-dy dx are on the right, so we can go ahead and factor it out. So when you factor that out, you're left with 3y squared minus 8y. So now you can divide by what you factored out, or what's left, and get dy dx alone. Would equal 5x to the 4th plus 12x cubed over 3y squared minus 8y. And that's your derivative equation. Okay, so let's try another. It has some mix up. So derivative of the first term. So you got to be careful here because this y squared is in parentheses, and this x squared is in parentheses, y squared parentheses, x squared parentheses. So you're going to have to use chain rule, right? So when you do the first term, the derivative of sine is cosine. Keep the inside the same, times the derivative of the inside, which would be 2y, and then you need to write your dy dx because that term had y. Do the same thing here, the minus, but then the derivative, I'll go ahead and show my work. Minus, and now the derivative of cosine is negative sine. Keep your inside the same, times the derivative of the inside, so 2x, and you don't need to write dy dx. Then you have your equal sign. Similar thing on this side. The derivative of cosine is negative sine. Keep the inside the same, times the derivative of the inside, times dy dx. Plus, notice when it's plus, I don't normally put a giant parentheses, but when it's minus, I do. It's kind of up to you. I noticed here I didn't close that either. Derivative of sine is cosine. Keep the inside, times 2x, and no dy dx needed. Okay, so now we need to clean this up. So I'm going to move this dy dx, because this is one term, over here, and I'm going to move this non-dy dx term over here. So I'm going to have to do plus sine y squared times 2y times dy dx to cancel that out. I'm going to do it over here. And then here, because that's minus and negative, I'm going to go ahead and say that minus, because that whole term is negative, like that's like a giant plus. So to move it to the other side, I'm going to have to do minus, right, sine x squared times 2x, because that was, does that make sense? That kind of looks weird, but minus and negative is plus, so to move it to the other side, you're going to subtract. So then I'm going to subtract over here. Okay, so then we are left with cosine y squared 2y dy dx plus sine y squared 2y dy dx equals, right, because these canceled too. What's left over here is positive cosine x squared 2x minus sine x squared 2x. I'm putting parentheses sometimes and sometimes I'm not. Okay, so last step, once you've collected all your dy dx on the left side, is factor it out. I wouldn't factor out anything else. Even though they both have a 2y, I would leave those until you move it over to the other side. you want to put it in the front, that might look more normal. I did not. Just factored out the dy dx. Everything else stays the same unless you want to rearrange your terms. And now we're ready to divide this whole thing. I should be ready then. This is getting repetitive to write, but we're almost done. So that would cancel, so then you do it over here, but you do not have to show this. If you just write the next step, you don't have to show what you're doing on each side. So if you notice, I'm going to kind of simplify in one step and write my final answer. I'm left with dy dx equals, now every single term on this side. So I have a 2 on the outside here, a 2 on the outside here, a 2 on the outside here, and a 2 on the outside here. All of those 2's would simplify, because you could factor out a 2 on the bottom, factor out a 2 on top, and it would divide out. So, and I'm also going to move these x's and y's to the front just because it looks more normal. So that's left with x cosine x squared minus x sine x squared divided by y cosine y squared plus y sine y squared.